Hello everyone, my name is Yuping Wang from Tsinghua University, China. It's my pleasure to introduce our work, ROS-SF. ROS or ROS operating system is a middleware that has recently been widely used in robotic systems, such as autonomous driving and even astronaut robots. Like other message passing middleware, the performance of ROS is crucial to the robot's reaction time. To support user-defined messages, such middleware usually serialize messages to binary stream before transmission, and after transmission, deserialize the received binary stream to messages. However, serialization and deserialization routines introduce time and space overhead, especially for large messages. Eliminating serialization would improve the communication performance, and such solutions are called serialization-free frameworks. Their basic principles is to directly construct and access messages as a serialized buffer. Existing solutions include RTI flat data corresponding to RTI connects PDS and Google's flat buffer corresponding to Google's protobuffer. However, because their interfaces are changed, developers have to rewrite applications in order to improve performance. Such code rewriting is unacceptable for the ROS community because there have been thousands of applications. So our goal is that can we enjoy the performance improvements transparently, that is, without the developer's effort of code rewriting. For transparency, we find that previous serialized message formats used by flat data and flat buffer cannot meet the requirement, so we design a new format, namely SFM. For efficiency, we carefully manage the life cycle of serialization-free messages to avoid copying operations. The first issue is our SFM format. The design principle is that the memory layout of a serialized buffer should be as similar as possible with the memory layout of a C++ structure, so developers can access fields or elements just like C++ structures. For example, this is a simplified image message defined in ROS, interface-defined language, and its corresponding C++ structure translated by the ROS tool is shown here. So, the memory layout of this structure is like this. And existing applications will construct and access it with such a layout. This is not a serialized buffer because it's not continuous in memory. The memory layout of our SFM format is like this. It's very much like a C++ structure because we know the offset of each element from the start of the structure. Either the content of encoding and the content of data can come first, depending on which is constructed first. SFM also support nested message, and more details can be found in our paper. As a comparison, this is the same image message represented by the XCDR2 format, which is used by the RTI flat data. The start of the height element, for example, depends on the length of encoding, so it is impossible to access it as a C++ structure. This is the same image message represented by Google's flat buffer, and it faces similar problems. The second issue is managing message life cycle. We carefully overload the message operations so that no memory is copied, leaked, double-freed, or used after free. Overall, here is our ROS-SF framework. Comparing with the original compiling routine of ROS, we add 3 modules. The SFM generator is used to generate message class that supports SFM format. The ROS-SF library is the common code managing message lifecycle, and the ROS-SF converter is used to ensure that messages are allocated on the heap. Here is an example. If we find a message object allocated on stack, we change it into a location on the heap with the equivalent behavior. To testify that our ROS-SF can improve performance transparently, we conduct 3 experiments. The first is the transmission latency between processes within the same machine. With the message size increases, our ROS-SF can significantly reduce the latency. If we compare this result with other serialization-free frameworks, we can see that our ROS-SF indeed reduces the latency of ROS to the same level of other serialization-free frameworks. But don't forget that developers need not to rewrite their code when using our ROS-SF. The second is for the inter-machine latency. We can get similar results. And of course, all the inter-machine latencies are longer than that of intra-machines. The third is an application case study with a commonly used robotic application, ORB SLAM. This application receives images from the camera of the robot and then locates the robot's coordinates and builds a sparse 3D map at the same time. The latency improvement seems small, but in fact, the absolute difference is similar with previous results. It seems small only because the application itself took about 30 to 40 milliseconds. And anyway, this case study showed that our ROS-SF framework can be transparently applied on practical applications. Besides, we conduct an applicability study because our ROS-SF can only work under 3 assumptions. The one-shot string assignment assumption, which assumes that there's no reassignment to strings, because an reassignment hurts the performance. The second is one-shot vector resizing assumption, which assumes that a vector is only resized once, because resizing the message multiple times also hurts the performance. The third is no modifier assumption, which assumes that none of the modifier interfaces, such as pushback or popback, are called, since they may trigger memory reallocation and hurt the performance. But in practice, we find developers do violate these assumptions, although this code style hurts the performance. When the first 2 assumptions are violated, we prompt a runtime alert. When the third assumption is violated, the code will fail to compile. We should note that other serialization-free frameworks implicitly assume more assumptions, and our ROS-SF explicitly reduces them to these 3. Okay, let me come to the conclusion. We present ROS-SF, a middleware which can transparently improve the message passing performance of ROS. To achieve that, we designed SFM, a new serialization format which keeps the memory layout of serialization-free messages as the same as regular messages. Source code and examples can be found in GitHub. Thank you.